Well, hello calculus students, and especially you seekers of truth. In this video, I am going to explain to you what's called the product rule of derivatives. It is an incredibly useful rule. We use it all the time in calculus, and I will explain this to you in terms of geometry to emulate the work of Isaac Newton. Everything he did in calculus is geometric, so we will approach it in that sense. But here's the problem formally phrased. Suppose we have a function a of x that is created by the product of two other functions. Our goal is to find a prime, or the derivative of a, in terms of the other two functions. It is not as simple as we wish it would be. And so, if we start out something like this, it's a prime, right? That's the derivative of a, is really equal to the limit as h, or I'm just going to call this delta x, right, approaches 0, of a of x plus delta x minus a of x. So we're just using the difference quotient that we've been very familiar with. Okay, so this is pretty straightforward, as straightforward as we can make it. And then we'll take it one step further. This is really equal to the limit delta x approaches 0. And instead of using a here, I'm going to rewrite it in terms of w and h. So this is w of x plus delta x times h of x plus delta x. In other words, whatever it is that we plugged in for a, we're going to do it the same thing for w and h, and then we're going to multiply them together, minus a of x, which is just w of x, h of x, all of this over delta x. Okay, so that's the approach to our problem, and this is going to become something very gnarly and very complicated algebraically, and it's going to be kind of weird to see how this gets simplified. It's going to be all this unusual steps, but it is most helpful if we can approach it using geometry. And so that's exactly what we're going to do. We will get back to this part in just a little bit, and once we figure out our final answer. But if you think of this, a of x is a product, and so we can just represent it as a problem of area, where a is the area of a rectangle, w is the width of the rectangle, and h is the height of that rectangle, and x versus delta x, you can think of this as time, right? So you can think of x as current time, and delta x is some small increment of time, so a small change in time. Okay. And you can look at delta w, delta h, delta a similarly. Delta w is a small change in width. Of this rectangle. Delta h is the small change in height. Delta a is the small change in area. Okay. And you can look at this too. W of x is the current width. So we're treating x sort of like time. Okay. And then w of x plus delta x, well, x plus delta x is sometime in the future. So w of that is just the width in the future, in some forward amount of time. Okay. And I put in quotes here, future here, because it just means a time that is further ahead than the time we're currently measuring from. Okay, so we can think of this, you kind of imagine like an animation, like this rectangle is getting larger and smaller. It's the width of it is expanding and the height of it is expanding at some rate, and we want to figure out how is its area expanding. Okay, and so here's how we're going to approach it. So let's say that the width in fact gets a little bit larger. Okay, so this section right here, this is nothing more than delta w. Okay. So that's the a small change in its width, and that the height gets a little bit larger as well, so that this section right here is nothing more than delta H. Okay? And then if you consider, and I apologize, I'm not drawing really well here. Let me see if I can draw straight lines a little bit better here. I'm doing it freehand. Okay, so this strip this length right here is how much wider the rectangle is getting. Here is how much larger the height of the rectangle is getting. And then of course this L-shaped object right here, that would be the increase in the area of the rectangle. Okay, so we'll call this region right here delta A. And let's just think about what all of this, how all of these variables are related to each other. Well, delta W, in other words, the change in width, a small change in the width, is really just equal to the width in the future, W of x plus delta x, minus the current width, right? So whatever the width is after it grows a little bit minus the current width gives you how much the width has changed. Okay. Same thing here, delta H. Let me rewrite it over here. Give myself a little bit more space. So delta H is just the H in the future, or the height of this thing in the future, W plus, this should be an X, H of X plus delta X minus H of X. And then if we look at this L-shaped region here, this kind of mirror image of an L, right? Well, what is it really? It's delta A, but that's just A of x plus delta x. So the area in the future minus the current area. And as you look at this, these terms here, they should look a little bit more familiar to you, and you can start to see their relation to the limit, to the derivative. Okay? And we're going to make this connection in just a little bit. Okay, so the key connection here, that what Newton saw when he worked through this geometrically, is a way to just reimagine the picture. So this kind of backwards L-shaped region is really a combination of this rectangle that I'm drawing here in red, okay, plus this rectangle that I'm drawing here in blue. Okay, so the backwards L, the green region, is really equal to just the red rectangle plus the blue rectangle. But how would we describe the area of the blue rectangle? Well, the area of the blue rectangle, this length right here, remember, is delta H. So the blue rectangle here. So the area of this is equal to delta H, right? This length multiplied by this length right here, which is just W of x. And now for the red rectangle, well, this area right here that has this dimension delta W multiplied by this whole length right here. Now this length is h of x, right, plus a little bit more, plus delta h. Okay. So this is times, or you can also say that h of x plus delta h, that's the height of in the future. So I'll explain that in just a minute. So this height here of this rectangle, it's not just the old height, it's the height plus a little bit more. So that's the height in the future. Okay. All right. So now that allows us to rewrite delta A. Well, what is delta A? Delta A is this blue expression plus this red expression. So let's combine that together. Okay, so delta A is equal to what I have here in green, but it's also equal to the sum of the blue and the red. So I'm going to write it this way. It is delta H times W of X plus delta W times H of X plus delta X. Okay. And so what that tells us is that the green expression right here and the purple are in fact exactly equal to each other. So now, if we look at it again, applying the difference of applying the difference quotient to the definition of the derivative, the limit stays the same. But notice this expression right here. That's the same thing as the green expression that we had up here. But that green expression is exactly equal to what I have here written in purple. So I'm just going to copy that down. So this is equal to delta W times H of X plus delta H times W of X plus delta X. Okay. All right. So I haven't lost the meaning of the limit. It's still delta, the limit as delta X approaches 0. All of this stuff here divided by delta X. Okay. So now you see that I'm getting a little bit closer and closer to being able to separate this out using the limit. And what I like to do though is convert everything into terms of W, H, or some combination of their derivative. So let's look at these two terms right here, delta W and delta H. Let's see if we can go back to our picture and find a way to simplify that a little bit. Okay, so let's look at delta W. Delta W is actually this right here, right? Delta W is really W of X plus delta X minus W of X. Okay. So that's worth highlighting, and all I'm going to do here is go back to my expression and make that switch. Okay. So what is delta W? Well, that's just W of X plus delta X minus W of X. And all of that gets multiplied by H of X. Okay. Similarly, what is delta H? Well, delta H is right here, right? Delta H is nothing more than H of X plus delta X minus H. Okay, so I'm going to swap out delta H here. This was H of X plus delta X minus H of X. All of this minus multiplied by the expression in purple. And don't forget, we're taking the limit as all of this as delta X approaches 0, and all of this is getting divided by delta X. Okay, so let's take a big picture here. What have I done, right? I've taken the limit definition of using A here. I'm treating A as an area question. I'm using my picture of the rectangle and manipulating some geometric properties of rectangles in order to make this expression much more complicated. So I got this stuff in purple that gets a little more complicated than the stuff I've written here in black, and then I've gotten the stuff in green, which is even more complicated. And it's very common and reasonable to wonder, why would you make things so much more complicated? Well, the beauty of mathematics, and especially calculus, is just as things seem like they're spinning out of control, if we're on the right track, we suddenly are able to make sense of it and simplify it very quickly. So let's see how that can apply here. Okay? And most of this just involves us applying very basic ideas. And the first basic idea is my ability to split this fraction. What is a fraction that's being added together except two other fractions with the common denominator? Okay, so I'm going to write the limit here so I don't forget it. And I'm going to split this fraction. The first fraction is going to have this denominator, and the second fraction is going to have the same denominator. Right? This is rules of adding fractions. So this stuff in the bracket, that remains. To be careful not to skip steps in my excitement here. Okay. And then same thing here, this stuff in the other bracket, that also remains. Okay. I'll put my big plus sign here. Okay. And the limit of a sum is also the sum of the limit. So I've broken this up into two smaller limits. Okay. And then, okay, all right, maybe this isn't too simple yet, but it will get better. Now I'm going to apply a second rule of a fraction, which is how do I multiply fractions? Well, note that the way we multiply fractions is just to multiply the numerator and multiply the denominator. So let's see. I'm changing colors here just so that we break up the monotony and the text doesn't all blend together. But I'm going to take this fraction here and split it into two parts. The first part is going to have a denominator of delta x, and the second part is going to have a denominator of 1. I'm going to put h of x over here, and then this stuff in the bracket over here. And let's see if I can squeeze this in correctly. The limit still applies here, and the limit as delta x approaches 0. Okay, so I've taken this fraction here and I've split it up, and notice the rule for multiplying fractions still apply. If I multiply these two fractions here, I get this expression that I have up here. There's a plus sign. And not so surprisingly, we're going to do the exact same thing with this. So it's going to be the limit as delta x approaches 0 of this first fraction, h of x plus delta x minus h of x. All of this over delta x, okay, times the limit as delta x approaches 0 of w of x plus delta x. And we can put all of this over 1. Okay, so again, if you kind of filter out the limits for right now and you just look at the fractions, they are precisely equal to this. Okay. And well, what have we accomplished? Right? We've made things really, really, really complicated, but now let's bring it home. Well, using the rules of limits, this limit right here, what is that really equal to? Well, that's just the derivative of w, otherwise known as w prime. Okay. The second term right here, we're taking the limit as delta x approaches 0, but there's no delta x in this problem, which means it's irrelevant. That whole thing is just going to be equal to h of x. Okay. The plus sign. This limit right here, I'm circling the stuff that's that's a little more complicated. H of x plus delta x minus h of x over delta x, limit as delta x approaches 0, that's nothing more than h prime of x, the derivative of h. Okay. And then this limit here, we're dividing by 1, so we don't have to worry about undefined terms or anything like that. If delta x goes down to 0, then this whole thing is going to disappear, right? And so what you're going to have left is w of x. And so now we've achieved what we wanted. We've taken the meaning of a of x, which is the function of our product. Okay, let's go all the way back up here, right? We're trying to find a prime of x, and we've taken this expression using our picture, taken it as far as we can. It turns out to be w prime times h plus h prime times w. Okay. Now, I should say that we use the geometric ideas of the rectangle here to make sense of our problem, but we're not limited by the rectangle idea. We could use this for just any functions at all, as long as it is two functions multiplying together, okay, the product of two functions. So this, in calculus terms, is called the product rule. It is something totally worth memorizing, although you don't have to try just yet. If you do lots and lots of practice problems, you're almost going to like automatically memorize them. All right, well, thank you for watching. I hope you've enjoyed this as much as I have. Ask questions if you need it, and have a wonderful day.